Morning, students. Today is December the 6th. Viva Quito! I would like to complete the explanation about how to use finite elements in order to solve plane stress problems. There are a couple of details here and there. I would like to close them up. And then I would like to see how you people are organized to start the group work. If there is some time, I would like to answer questions. Oh yeah, we have to organize that because we have to assign the values, the proportions for to complete the assignment. So everybody will have different values. Yeah, okay, that's about it. Let's see if we can share the screen. Okay. Can you see my screen, my PowerPoint screen, Isaac?
Yes, sir.
Okay, thanks. Okay, so we were back here. Okay, so we said that we're going to use triangular elements in order to partition our domain. Our domain now has 2 dimensions. It's a little bit more complex than what we had before. In this case, we use the simplest element, which is a triangular element defined with no joint values at the corners, 3 corners, of course. So we could use a polynomial of which includes 3 terms. So we decided to use this linear polynomial, but in 2 dimensions, x and y. Immediately, we see that this selection of the polynomial for interpolation in each element brings us several simplifications. One of them is that the first derivative is a constant. So immediately, the first derivative of this is going to be the strain. So the strain is going to be constant in every element. That's the reason this element is called CST, constant strained triangle, okay? So in order to find this constant, what we do is we evaluate this interpolation in each one of the 3 corners. So we have a set of equations, 3 unknowns, A1, A2, and 3 are the unknowns. We find them and we replace in the original expression, and then we rearrange this in this way. See, everything which is multiplied by UI, that's the displacement at I joint, is called NI. Everything multiplied by UJ is here, and finally by UK is NK. Okay, and then we see that there is some particular way these coefficients are presented. Constant X, constant Y. And these functions were presented in the example that I shared with you. Where are you? Here. I need to stop sharing this, right? I need to share my screen again here. So this is what we did next in the last class. This is the way I was telling you we use in order to present the polynomial for interpolation in every element. These are the way or the shape, the mathematical form that each one of these polynomials take, constant, constant x, constant y. And here you can find you can see the formulations to evaluate each one of these each one of these coefficients. Something which is very important is the way we number the numbers, okay, the joints. So every joint, every element has to be named with 3 joints, of course, and this is the way these 3 joints has to be numbered. See, that's the counterclockwise, okay, because we need to do some operations and we rely on that. So please be careful with this. Once we have that, we can go on and deduce an expression for the K matrix in this case. Before that, one of the things I was explaining last class was that in this type of problems, since we are working in the plane, both dimensions in x and y are important. That means that every point can move in the x and y direction. So what we do is we produce 2 interpolations, one for u and one for v. But both interpolations follow the same polynomial. Okay, so we use the same nij to interpolate u and also v. Of course, for u, only the u values participate, and similarly for v, only the v values participate. So for every joint, okay, this joint can move in the x and in the y direction. Similarly for the other 2 joints. So this is a vector with the displacements of the joints of one element. And this is 6 rows and 1 column, of course, since it is a vector. Okay, now we remember these 3 values, epsilon, that we need in order to evaluate the strain energy. So this is the derivative. So if we differentiate that, we get beta I divided by 2a. So everybody will have a 2a, so I put it down here. So the derivative of this will be beta I times ui plus beta j times uj plus beta k times uk. And that's what you see here in the first line, multiplied by this vector. Similarly for dv dy, that's epsilon y, and similarly for gamma xy. So here we have a vector with the 3 components of the strains that we're going to use. This matrix here, we call it B. So this at the end is going to be B, matrix B times the vector D. Okay. Something which is very important, I put it in red, is that inside every element, this is the strain. You see that it is just a constants, 3 constants. So inside every element, we mentioned a few minutes ago, the strains are going to be constant. And that's because that's the type of interpolation function that we employed. If we multiply this vector of the strains times this matrix, in the case of isotropic uniform material, we obtain stresses. Of course, the 3 stresses that we mentioned before. Okay, E is Young modulus, nu is Poisson ratio. This matrix, we call it D. So finally, we can say that the vector of the sigmas is equal to matrix D times vector E. And this vector E here from up here is equal to the product of matrix B times vector D. Right. So here we have this is an expression that we recall from ship structure, that's last semester. To obtain this as a scalar, we can multiply this vector, this row originally epsilon was a vector and we transpose it. So we obtain a rho multiplied by the vector of the sigmas. Okay, so what we have to do is to obtain this, is to get this and transpose it. So we obtain this, and this, we take it from here. So finally, we do all this replacement, and this is what we obtain. Okay, so it's like having a d squared times something. So it's in a general way to explain it, okay? We could say that this is like having something k times d squared and divided by 2, because I have d here and I have d here. So in order to obtain the static equilibrium, remember, what we have to do is we have to get the minimum of the potential energy. So in this case, what we're doing is express U as function of the D. That's the joint displacements. So what we can do is we try to find the minimum if we change the values of the displacement, joint displacements. That's what we're doing here. So we differentiate with respect to this vector. This is not a precise operation. What we have to do, we should differentiate this with respect to ui, then make that equal to 0, then with respect to uj, etc. And at the end, this is what we obtain. This is what we obtain. So all of this is a matrix, and this is what we call the K matrix. So the K matrix is going to be TA here, and here in the B's, I have 1 over 2A. So I cancel this A with one of the A's in the denominator, and I have 4A here. The thickness is here, and the rest is here. As I said before, we could establish these 3 matrices and make this multiplication, or we could just leave it like this, because it's a very long expression to type, okay? If you have the time to type it in Word, please share with me that expression. I will include it in my class notes. I didn't have the time. Okay, so far, people, is there any question? Is there any questions about this? Mr. Alarcón, do you have any questions about this so far? Mr. Alarcón is here?
No, doctor. Good morning.
Everything is clear?
Yes.
Crystal clear. Come on, that should be a question somewhere. Anyway, I'm glad. Yeah.
I have a question. For this term in the first part in the K.
This one?
No, to the left.
To the left, this one here.
Yes, we can
Okay.
consider this is the stiffness or the element or not?
No, the whole thing is the stiffness of the element. The whole thing.
Okay.
Not only this, the whole thing. The whole thing. Since we are here, why don't we check the units? Ms. Lopez, what units should we get for K? Ms. Lopez, what units do you think we need for K? Don't do it, just by definition.
Definition.
By definition. Come on, somebody. Mr. Zamora, what units would you expect for K? Mr. Zamora? What? I'm sorry? What units would you expect for K? Mr. Zamora? No? Mr. Matut, what? Force?
Force over
Force divided by what?
longitude.
Exactly, exactly. And that's because by definition, you multiply K times D, that's the displacements, and you get force. So K should have units of force divided by length, over the length. Okay, let's see if we get that. So here, I have some terms multiplied by ET over 4A. Now, we have to be careful because I have beta and gammas in here again. So let's check what are the units of beta and gamma. Let me go here. So beta is here, gamma is here. So both have units of length. So let me go back here. So here, the result of these are length. This is non-dimensional, and this is length. Here, I have E, which is F divided by length squared, the thickness, area, there. A nu, of course, is non-dimensional. So we have 1, 2, 3, and have 4. So the result is going to be F over L. Remember, this is extremely important. Every time we do this calculation, we should be careful with the units. Okay? Fine. Then we presented an example, which is here. Okay, so we have this is like a flat bar. Okay? And we fix it here, and we put a concentrated force up here. Now, please remember that this case, we are not taking the kinematic assumption. Okay, so we're closer to what we do in elasticity. We are not taking this assumption. So we do. I just wanted to show you the very general procedure. So we took this partition, 4 elements, okay, and we see that there is some parallelism between elements 1 and 3 and 2 and 4. Okay, this is our connectivity table, and you see immediately that every element is defined with 3 joints, which are named in the counterclockwise direction. For example, element 4 is 263, 263. So we have obeyed our previous convention. 1 centimeter in thickness, this is very important too, there. So here, I have a little, this little scheme to keep in mind our partition. We're going to work with elements 1 and 3 at the beginning. So I have this joint, and that joint. Those are the positions. Okay, 0, 0, this one here is 100 and 0, and this one here is 150, 150. And from these values, we get alpha, beta, gamma. Of course, and with these values, we can also calculate the area. Now, this is the operation that we have to perform in order to get a K matrix. So I have beta transpose D and B. So this thing here is the result of the product of these 2 matrices, D times B. And finally, I have to multiply this times that. This thing here has 6 rows and 3 columns. This has 3 columns and 6 rows. So the result is going to be 6 by 6. Okay. In another operation, not here, in another thing, see, somebody wrote something like this. This times that. For example, in this case, this is a vector which is going to be 6 by 1. And this is a matrix which is 6 by 6. can you complete this operation, Mr. Matute? Mr. Matute, could you complete this operation on the top left of my screen? Mr. Matute? Not here, Mr. Matute. Ms. Pinkai? Ms. Pinkai, can you perform this operation, this matrix operation? No? Ms. Pinkai doesn't want to hear about me. Mr. Nevares, can you perform this operation? Mr. Sanchez, can you perform this operation?
Good morning, doctor. Yes, I think.
No! No!
Oh, sorry.
No, I'm sorry, I didn't show the screen. I'm sorry. I didn't want to disturb you. The problem is why you cannot solve, complete this operation? Somebody, anybody, please tell me.
The dimensions are according to it.
Exactly. What should be the dimensions in order to be able to perform this? This number here has to be equal to that number there. So this operation here cannot be performed. So we have to be careful in the way we write these things. Okay, and that's what you see, that every time I'm trying to remember about the number of rows and columns, because it's so easy to get confused. Okay, so I'm just checking myself in order to keep track of my operations are correct. Okay, and finally, this is the operation that I have to perform. This is the product. This is this. And finally, I have elements 1 and 3 and elements 2 and 4. This is the K matrix for 1 and 3 because you can see that the proportions are the same. In this case, I depend on beta and gamma. And remember that beta and gamma are differences in Y and Z's, in X and Y's. Here, beta, difference between Y's, and gamma, differences in X. So if I define this element, see, element 1, like this is the I joint, this is my J, and this is my K. And I define element 3 with this is my I joint, this is my J joint, and this is my K joint. In this case, the differences in X and in Y's are going to be the same, okay? So this matrix is the same, this matrix is the same material, so everything will be the same, and the K matrix for elements 1 and 3 are going to be the same. Similarly for elements 2 and 4. So this must tell you something about the way we can define the elements in order to save some space. Okay, and the rest is we have some experience. Okay, forming the global stiffness matrix. Okay, in this case, what I'm doing is I'm taking element 1, okay, and I'm placing that into a big K matrix filled with zeros. Okay, so this is the K matrix, the big K matrix, considering only the first element. We can do the same for element 2. So this is the big K matrix, considering only the second element. Similarly for the other 2, and what we can do is now, since we have a 12 by 12 global stiffnesses, one for each element, what we can do is we can simply add. Okay, we can simply add, and this is what we obtain. Now, here, this and this are clamped. So we have something like this. So this thing here cannot move in neither direction. Similarly for this. There. Remember that these elements are clamped. So you remember that the slope here is 0. So we're saying that this joint cannot move in the vertical direction. But we should do something more. We should put another joint here and consider that this joint cannot move either. Okay? In this way, we have two points which do not move in the vertical direction. So we are certain that we're assuring that this is horizontal, and then it starts the deflection. So you see that when we start working with these 2D problems, we get more interesting things to consider. Okay? So this is something that we should keep in our. Yep. Yep. Somebody has a question? Go on, please.
Yes, there is an order to place the node for example, is we have an element and we make partition up and down where we should first place the nodes up or down.
Would you please repeat that, because I'm not following you. When you do partition, you place joints which help you to define elements. And then you go on with the locating the forces and establishing boundary conditions, support conditions. So since you know what these boundary conditions are, what you try to do is you go back and try to establish a partition in such a way that you can apply the boundary conditions adequately. For example, if you have a joint where you know that this point receives a force, or you have a point where you know that there is some support, then you try to include there one joint in order to apply the boundary condition. Would you please repeat that, your question, please? If I don't know if I try to.
If we have an element and we make a partition up and down.
If we have an element, for example, element 2. Okay, this is an element. Go on. Now what? If I have an element, go on.
Yes.
And then, what's your question? If I have element 2, go on.
We have two partition up. Is the
in this direction? Up.
Yes.
You could have more a different partition. I'm going to share in a minute. I'm going to talk about convergence. For example, this is your domain, right? There are two important things here. First, here, this is clamped, and here I have a force. So these are the two most important characteristics. So what we could try to do is to try to represent adequately this side and adequately this, because here we are going to have the application of the force. So these are the main two characteristics that we have to have in mind. So what we could do is we could try to include more elements in this area. For example, let's try to do something like this. See? And here, we could try to do something like that. You see that here, elements are smaller, and you can see a more decent variation. And here, you could try to do something like this. In this case, you have more elements in the vertical direction. And in this area, you see, and in this area, you see that the elements are smaller. And remember that the problem is that, let me show here. Okay, let's suppose that this is the correct solution. It includes curvature, right? What we're doing is partitioning this domain in these points with these elements. And then we're trying to approximate with straight lines. So in this area around the foundation and around the place where you apply the force, of course, you expect a larger gradient than in the central area, right? So what we can try to do is include more elements, okay, in this area where we have the support. And yes, after this element, you can have more elements in this in the upper direction. Similarly for this area. And I don't remember the name of the person who's talking.
Welcome.
Oh, Wakon, yeah. More or less, Wakon?
Yes, doctor.
Okay, no problem. So yeah, that's something which is very important with finite elements, okay? Remember, you all studied this, for example, we could use finite differences, okay? Finite differences. In this case, we have this. If we want to partition this, in this case, for example, if we want to include this as the dimension, then we have to do this. Okay, so in this case, we have to make it like this. So this is our system. Why? Because we can only use quadrilateral elements, partitions. Okay, we have the flexibility of finite elements. For example, if we need to do something like this, to analyze something like this. In finite elements, it's easy. You do something like this and that's it. In finite differences, all what you can do is you have to do something like this. Because your elements have to be square. So we get more flexibility here. That's one of the advantages. But of course, the formulations in some cases are more complex. Of course, nothing is for free. Okay.
Doctor,
yeah, go
doctor,
on.
The partition must not be the same.
No, can be very, very different. That's the advantage of this process. See, the partition is, for example, let's suppose that you want to analyze this case. Of course, you can imagine that around this area, the stresses are going to be very large. So what you can do is you can try to split the domain like this. Okay, we can go like this, and then we include elements like that. These elements are smaller. You know that in each one of these 4 elements, okay, in each one of them, the strains is going to be the constant. So it's a good idea to make a partition like that, or more efficient, for example. We could do a partition like this. There. So you see that you have more elements in this area and the smaller when in the place where you apply the force. So in this case, you can calculate in a better way the distribution of stresses around this area. If this is the area where you want to analyze the stress distribution. And then you can increase the size as we have done here. Otherwise, okay, you can say, I can take this size for every element. But the problem is that you are going to increase the number of elements and the number of joints. And of course, the size of this matrix will be very large. Okay, and for example, Isaac is doing right now his thesis using these things. How long does it take for you, Isaac, so far? How many minutes?
When I use the element size of 5 millimeters, and this around the half hour.
Half an hour. Can you imagine? You put the run, and you have to expect 30 minutes in order to get an answer. That's because the elements are so small that you have a very large stiffness matrix, global stiffness matrix. And you have to solve it, and he does iterations. So in every iteration, that's what he has to solve. So yeah, you have to be very efficient in trying to partition your domain in such a way that it represents adequately the high gradients in the areas where you expect to have a large gradient, and in the areas where are very apart from that, you can increase the size of the elements because in those areas are not that important. Mr. Wakon?
Yes, Dr. Thanks.
Okay. Oh, no problem. No problem. Okay, here, before we go to the break, you can recognize the large values for U1 and V1, and for U4 and V4, which must be 0. These are the external forces downwards, and the process is standard. We solve it, we check equilibrium. Oh man, I forgot to check these values. But this is something that we always should do. And then we go every element one by one. This is the definition of the stresses. So this is what you have to do in order to get the stresses. Again, here, before we go to the break, see, this beta has units of length. This displacement has units of length. A is F over L squared. A is length squared. So we cancel this, and we have the units of stress. So every time we do these calculations, every time we should do checking units, okay? This is for element 1. So what we're saying is that in element 1, see, in all of this part here, we have a sigma x, which is compressive. So we have stress like this. It's uniform. In element 2, we have it up here, down here, I'm sorry. We have the same value, but you see that this is positive. Does that make sense? Does that make sense? Mr. Zambrano, does this make sense to you? Mr. Zambrano? Miss Freire, does this make sense to you? Miss Freire, no? Mr. Carrillo, does this make sense to you? This distribution of stresses? Yes.
This is line.
Does this make sense to you? Yes and no, and why? Does this make sense to you?
Yes.
Why? I have a force here. So it's, but yeah, why? I don't want yes or no. I want a reason. I can say no, but the thing is that
beam bending.
Exactly. In the upper part, what do you expect in beam bending if you have a concentrated force on the right? And this is clamped. So you will have something like this. Right? So in the upper part will be tension. In the lower part, you will have compression. So it makes sense to have this is negative and this is positive. Makes sense. Now, you see that it's very strange, right? Because I have in this triangle, I have to the left, in the upper triangle to the right. Yeah, but this has more area. So I can think that it's like having a net, in this area, I have a net force to the right. I have a net force to the left. And the combination of the two will give you the bending moment. So it makes sense. Okay. We will see this when we return from the break. Okay, okay, let's take a break here. And when we return, we will go over these general instructions to use this program. I hope you took some minutes in order to review them. And then we are going to say a couple of words about the project. Okay, so 5-minute break, people.